Hello and welcome to video NL2, Friction and Drag. This video looks at what happens when we include friction in motion and how this affects Newton's laws in particular. It goes along with the beginning of chapter 5. Keep in mind that friction acts in the direction opposite of the body's velocity. Also that the magnitude of the force of friction is dependent on the surfaces in contact. We're going to talk a little bit more in particular about what about the surfaces it depends on in just a few minutes. When we are looking at friction, we break it into 3 different categories: statics, rolling, and sliding. Statics is, of course, when we're talking about things that are not moving. So when we start to push on things, but it's not quite enough force to get it to start moving. And rolling and sliding are as they seem. It's when objects are in motion. And this video in particular is going to focus on sliding friction, which we call kinetic friction. So in other words, we are not going to get into the details in this video about what happens if you have a ball rolling down the hill. Instead, we will just be looking at it when it's sliding down the hill. The equation for finding the force of friction is, as you may remember, hopefully you remember from regular physics, force of friction is equal to mu sub k times the normal force. And keep in mind, mu sub k is the coefficient of kinetic friction. It depends on the surfaces that are sliding and is a characteristic of the material. So each material has a different mu sub k. However, it can change if the material gets wet, or if it dries out more, or if it has been sanded or not, or all sorts of other things that you can do to a surface. We will most often deal with these as constants. So if we take a look at this chart here, it shows the coefficients of friction, both static and kinetic friction. As I said, we're going to focus on the kinetic friction in this video. When we're talking about 2 different surfaces that are together, or 2 surfaces that are touching, like wood on wood, we go down to rubber on other solid surfaces. Coefficient of kinetic friction is 1. It's quite high. Whereas if we put Teflon, for example, on steel, then it's 0.04, quite small value there. So there's the range for it. The coefficient of static friction is used when the objects are pushing against each other but are not yet moving with respect to each other. It increases as the forces applied increase until it reaches a maximum. And the value in this chart in the left-hand column here are the maximum values. It is at the point at which the object just starts moving once the coefficient of friction and the forces get large enough. So let's take a look at an example. A skier has just begun to descend a 30-degree slope and discovers the snow is slushy. As a result, he travels down the hill at a constant speed. What can you determine about the coefficient of friction? Well, in order to approach these problems, they are talking about forces and forces interacting with each other, so we really need to start with a free body diagram. So if we've got a hill at an angle of 30 degrees. The forces on the skier are going to be his weight, friction, and the normal force. Now, keep in mind that the skier here, the pictures doesn't show it tilted quite as much, but we still have the same thing, the weight going straight down, normal force going perpendicular to the surface, and then friction going up the hill. If we take these 3 forces and apply it to our angle without the person in the middle, we can get a little bit more detail out of it. So we have our normal force, the weight of the skier, and the force of friction due to the snow. Now keep in mind that the force of friction due to the snow is equal to mu sub k Fn. So if we take a look at this, if this is the force diagram for this skier, and the skier is traveling at a constant speed, that means that the sum of the forces in the x direction should be equal to 0, and the sum of the forces in the y direction should also be equal to 0. So we can break these down into x and y coordinates. We can also come up with, well, what is our x and what is our y plane? And if we want to think about this, we are going to save ourselves a lot of trouble and difficulty if we tilt the coordinate system so that it matches with the plane of the hill. So perpendicular to the hill is the y, and along the hill is the x. When we do that then, and when we keep in mind that, again, we are talking about forces, so we want to talk about the force from Newton's second law, F equals ma. The sum of the forces in the y direction are going to be the normal force minus the force of the weight in the y direction, which we can quickly determine as being this component here, and that is normal force minus mg cosine theta, which, again, as we said before, is going to have to equal 0 because there's no acceleration. The sum of the forces in the x direction will be found similarly. This time, however, the normal force only acts in the y direction, so we don't have to worry about that. But we have the x component of the weight of the skier here, and we have the frictional force. So the sum of the forces in the x direction will be the weight of the skier minus the force of friction, or rather the weight of the skier in the x direction. So we get mg sine theta minus mu sub k Fn is going to be equal to 0. So we look at these two equations, we see, oh, there's an Fn in both of them, there's m's and g's in both of them, but the Fn in the first equation makes it easier for us to solve this. So if I solve the first equation for Fn is equal to mg cosine theta, plug that into the second equation, and what I end up with is that mg sine theta minus mu sub k times mg cosine theta is equal to 0. Solve this for mu sub k. I can cancel out my mg's on each term, and mu sub k becomes sine theta over cosine theta, or simply tan theta. So what this tells us is that the coefficient of kinetic friction when the skier is going at a constant speed is only going to be dependent on the tan of the angle. Well, we know that the angle of the hill is 30 degrees, so mu sub k then is tan 30, which is 0.58. Now remember, because mu is a coefficient of static friction and it's essentially the ratio of forces, it has no units. So even though this appears like it might be a difficult problem because we've got something at an angle, if we think about it in terms of breaking it down by the components, we can see that we really end up with quite a simple relationship here. This actually will work in some other situations that we will come across as well. Let's look at another situation, again on a slant, but this time with a couple of different objects that are intersecting with each other. A box of MA equal to 10.0 kilograms rests on a surface inclined at 37 degrees to the horizontal. It is connected by a lightweight cord which passes over a pulley to a second box of mass MB, which hangs freely as shown. If mu sub s is equal to 0.4, what range of values for MB will keep the system at rest? Okay, so let's think about this for a second. First of all, we have theta of 37 degrees. Next, we are told MA is 10 kilograms. MB, we don't know what it is. Now notice it says we want a range of values for MB, because remember, we're talking about static friction here. So the mu being 0.4 indicates that the force could be from 0 up to a certain value. So let's start again with looking at a free body diagram for this. On mass A, we have a normal force. We have the weight. We also have a tension force. Now, in this case, even though we are trying to have the MB keep the system at rest, if MB gets too big, the box is going to come up the hill. But until that point, the box is going to have a tendency to slide down the hill. So the force of friction, the last force on this, is in the same direction as the tension, even though that may seem a little bit backwards. So if this, in fact, is the case where we are looking at the situation where M2 is 0, or is significantly small, and M1 will slide down the incline, then it will be pointed up. But if M2 is large enough, M1 will tend to be pulled down the plane, so the force of friction will go the other way. Okay, so this, I'm going to call this force of friction 1, and this is for not 1 and 2. So for force of friction 1, the mass of B must be super small, 0 or small. And I'm going to put in dotted force of friction 2, which is when MB is large enough. For both of these cases, Newton's second law for the y direction perpendicular to the plane is the same because there's no y motion. So we can look at the y, and we end up with the normal force minus MAG cosine theta. Again, there's no motion in the y direction perpendicular to the plane, so these are going to have to add up to 0. And keep in mind, of course, that this is also Newton's second law, so MA times A in the y direction, where MA being the mass of box A, but then the acceleration in the y direction. So we can simplify this, and we can then say that the normal force is equal to MAG cosine theta. If we consider both cases, let's start with the first case, however, we have the following situation where MAG sine theta minus the tension force minus the force of friction is going to be equal to MA times the acceleration in the x direction. For this particular case, we want the acceleration in the x direction to be 0 because we don't want it to go anywhere, right? We want to keep the system at rest. So we want this to go to 0. Since the force of tension is related to the second mass, MB, and that's the value that we're looking for, we can replace the force of tension by saying, well, really the force of tension is just the weight of B. So I can change this equation around a little bit more and say then that MAG sine theta minus the force of friction needs to be equal to the tension force, so it's sitting still, which, as we said before, is the weight of box B. The most that our force of friction can be is mu sub s Fn. Now remember that Fn is the normal force on box A, so the most that can be would be mu sub s MAG cosine theta. All right, so with all of this information, it appears that we have enough to simplify this equation. We have MAG sine theta minus mu sub s MAG cosine theta is equal to MBG. They all have g's in it, so let's cancel out all of our g's here. And we end up with MB equaling MA sine theta minus mu sub s MA cosine theta. Okay, so if we plug in the numbers that we know, MA is 10, and that's in both, so I'm going to pull that out, times the sine of 37 minus 0.40 times the cosine of 37 degrees will tell us that the mass of B is 2.8 kilograms. Now remember that this is a mass of B that will make it so that we don't want the acceleration here. If MB is less than 2.8 kilograms, box A will slide down the incline. All right, so we know that MB at a minimum is going to be 2.8 kilograms. Now we need to do the other situation to find out what happens when we have MB being large enough that it will tend to be pulled upwards. Okay, so for Newton's second law, when MB is large, we have that MA G sine theta plus the force of friction minus the tension force is equal to MA in the x direction, which again we want to be 0 because we don't want it to go anywhere. And this will give us the maximum value M2 can have without causing acceleration. And again, do this by solving for the force of tension like we did previously. Ft will be MBG, or the weight of the second mass, and that will be equal to MAG sine theta plus mu sub s MAG cosine theta. Get rid of the g's as we did before and find out that MB will be MA sine theta plus mu sub s MA cosine theta. So notice that this equation is almost identical to the one we started with over here. It's just that this one has a plus in it and the other one had a minus in it. If we plug the same numbers in and solve, we end up with MB equaling 9.2 kilograms. So the range of values for MB is that it must be between 2.8 kilograms and 9.2 kilograms in order to keep box A constant at a rest on this incline. So this is what has to be the case when we are trying to keep an object at rest and we know what the static coefficient of friction is. But what happens if we want the object to move and we know that the coefficient of kinetic friction is 0.30, and let's just say for the sake of symmetry that we put MB to be 10 kilograms as well, similar to what we had for MA. Let's see what happens in that case. Let's say that the coefficient of kinetic friction is 0.30, and we know that the hanging box is going to have a mass of 10 kilograms, just like the one on the slide is. Now the question is, what is the acceleration of the system? In this case, M2 will fall and M1 will rise up the plane this way with some acceleration that we want to know, and this will go down. If that is in fact what happens, then the acceleration can be given by the following equation based on, again, Newton's second law, that MAA is going to be the tension force minus MAG sine theta, because there'll be some part of the weight in the opposite direction of the tension force, and minus the kinetic friction. Since MB also accelerates, we can also have the equation that the force of tension, which is MBG minus MBA, since B also accelerates, we have the tension force being the weight of B minus the acceleration of B. And that's because they're in two different directions. And so we can substitute this into this FT into the equation above, and we end up with MAA is equal to MBG minus MBA minus MAG sine theta minus mu sub k Fn. We solve for the acceleration, and of course remembering that our Fn over here, our normal force, is equal to MAG cosine theta. We can plug that in as well. And when we rearrange that, we end up with the equation that acceleration is equal to MBG minus MAG sine theta minus mu sub k MAG cosine theta all over MA plus MB. Plug and chug our numbers here. MA and MB are both 10. Makes it lucky for us in this point. And we end up with 10 times 9.8 minus 10 times 9.8 times sine of 37 minus 0.30 times 10 times 9.8 times cosine of 37 all over 20. We solve that and we find out that the acceleration of the whole system, when both of the blocks are the same, is 0.78 meters per second squared. So the key to solving this problem in this particular case is keeping in mind that since there is an acceleration, Newton's law, F equals ma, is going to have to be applied to not only the first object on the slide, but also to the second object, because they are linked together as part of one system. If we didn't have any friction on this, then we wouldn't have to do half as much work, but friction gives us a more realistic situation to deal with and a more realistic situation to analyze. In the last two examples, the objects involved in the situations were two solids. When one of the objects is a fluid, then we get slightly different results. Even though friction still exists, we are dealing with a couple of different concepts. When we're dealing with really small objects and small speeds, we are talking about something called drag. And drag is the resistive force that objects feel as they travel through a fluid. So we just call it drag instead of friction, really. And if we are talking about small objects and small speeds, then the force of the drag is usually equal to a negative BV, where the negative is indicating that it is an opposing force, and the B is a constant, depending on the viscosity and the size of the fluid and the object. And you can see here what I'm talking about. If this object here is falling through air being a fluid, then we have the weight of the object pulling it downward, and the drag pointing upwards of a negative VB. At high speeds, then the force of the drag is proportional to V squared as opposed to V. So when we're looking at this and we're trying to figure out what that does to the speed of the object or the velocity of the object as it's falling, you can see as the object starts its descent with a 0 speed, it will be accelerating due to the acceleration due to gravity, but its acceleration is decreasing because as its speed goes up, so does the drag. And so this is a give and take sort of situation where as gravity is pulling down and trying to make it go faster, the drag is trying to slow it down. Again, small objects and speeds, the drag will be proportional to the speed of the object. If it's high speeds, then the drag is proportional to V squared. If we are considering an object falling from rest through air or another fluid with gravity and the force of drag proportional to V, then the sum of the forces on the object are going to be the weight of the object plus the force of drag, which would then be able, we could look at it as saying, well, that's really mg minus bv. Keep in mind that the sum of the forces is also able to be looked at as Newton's laws, so it equals ma, and the acceleration, remember, is dv dt. So if the sum of the forces is mg minus bv, and it's mdv dt, then that means that those two are also equal to each other. So if we look at when t equals 0, we know that the velocity is 0, so the acceleration then is simply dv dt, and we know at that point that that would be gravity. Now, as time increases, we know that the velocity also increases, but acceleration decreases. And remember, acceleration decreases because your drag force here, negative BV, is getting larger, and it is headed towards the same value as the weight of the object, mg. When we get to the point that BV is equal to mg, or mg minus BV over here in the equation is equal to 0, then dv dt equals 0. At this point, there is no acceleration. So let's see, how do I want to write this? So BV goes to mg, and when BV is equal to mg, dv dt equals 0. And at this point, we have reached the speed called terminal velocity. So terminal velocity is when the object is going as fast as it can, and the drag force is equal to the weight of the object. BV is equal to mg. We can write an equation for terminal velocity by using the equation that we have down there on the bottom, and it turns out that our terminal velocity then is simply when you have mg over b. So we could calculate what our terminal velocity is if we know that constant that is related to the drag force. So let's actually do that now. Let's go ahead and come up with an equation that shows us that the velocity, terminal velocity, is in fact mg over b. So determine the velocity as a function of time for a body falling vertically from rest when there is a resistive force proportional to v. All right, well, we're going to start with an equation we had on the last slide, which is that dv dt is equal to g minus b over mv, which is essentially just the original F equals ma equation. In this case, there were two variables, v and t. we collect variables of the same type on one side or the other of the equation. And let's put t's on one side of the equation and v's on the other side of the equation. So we end up with dv over g minus b over mv is equal to dt. Now, I want to rearrange that a little bit more to get rid of that b over m because it's going to be important in a little bit. So we can rearrange this a little bit more, and this becomes dv over v minus mg over b is equal to negative b over m dt. Now, if we integrate both sides and we remember that v is equal to 0 at t equals 0, we can integrate from 0 to v and integrate from 0 to t. We end up with natural log of v minus mg over b minus ln of negative mg over b, and that is equal to negative b over mt. We can combine the left-hand side, and we end up with ln of v minus mg over b all over negative mg over b is equal to negative b over mt. We raise each side to the exponential, and that will allow us to get rid of the e, and then we end up with v minus mg over b is equal to a negative mg over b e to the negative b over mt. I'm going to move the mg over b over and pull it out, and we end up with a neater version of v equaling mg over b times 1 minus e to the negative b over mt. And this relationship here tells us the velocity as a function of time, and it corresponds to the graph on the last page where it was like this, and we had time on the x-axis, velocity on the y-axis, and we had our terminal velocity here near the top. Now we could go ahead and check this to show that at t equals 0, the acceleration is dv dt, and the acceleration ends up to be gravity. I'm going to assume that you can do that, however, so I'm not going to spend time doing it. But let's take a look at what happens at large t. At large t, the e to the negative b over mt approaches 0. So the velocity approaches mg over b. So again, at large t, this term here approaches 0, and velocity then approaches mg over b, which is the terminal velocity that we had just come up with on the last page. If we set a time constant to be tau, which is equal to m over b, this time constant will tell us the time required for the velocity to reach 63% of terminal velocity. And when we do that, we can end up then getting a velocity equation that's a little bit more compact than what we have written there. And that is that v is equal to vt times 1 minus e to the negative 1 over tau. This equation for velocity, and therefore for terminal velocity, is typically the equation for velocity as a function of time that we actually deal with. Now, why do we use tau as being m over b? Because it works. And why is the m over b the time required for the velocity to reach 63%? Because e to the negative 1 is 0.37. And so when you end up with e to the negative 1 here, on the equation, that's 0.37, so the opposite of that would be 63%. We will use this idea of terminal velocity and this relationship between velocity and time in class, not only when we are discussing terminal velocity, but also with respect to a design lab that you will be doing. So bye for now.